Hello, this is our second lesson on vectors for pure core maths in Year 12 further maths. And what we're looking at is how to get a vector equation converted into a Cartesian equation. These are Cartesian equations. This is actually a three-dimensional Cartesian equation. Normal Cartesian equations might look like this: y equals 2x plus 1. You'll notice how there's an x and a y, and you should know the straight line graphs of these even, that they look something like this. They've got a gradient here, that's meant to represent a gradient of 2, and it's meant to suggest it crosses at 1. That's why I'm saying it's y equals 2x plus 1. But sometimes you have three-dimensional graphs, and when you have a three-dimensional graph, sometimes they label them x, and y might even sort of come out of the page like this, going backwards like that. That might be y, and then z might be going upwards. And annoyingly, x, y and z axes can be drawn in a whole host of orientations. So just because these ones I've drawn like this, sometimes they do x, y and z goes in and out. But we have to be able to deal with these equations of lines, and I'm saying straight lines, because they're the simplest ones. So start off, I've got this statement at the bottom. It says if two vectors a1, a2 and b1, b2 are perpendicular, then you can multiply together the top numbers and the bottom numbers. And when you do that, you get an answer of 0 if they are perpendicular. Now, this is actually something called the scalar product, which we'll come on to in due course. But for now, it's just good enough to know this fact. So it says, explain how you can show whether some of these pairs of lines are perpendicular. Now, first of all, notice this doesn't matter. The 2 one, I could have 20 and 10, or 4 billion and 2 billion. It wouldn't matter. What matters is this thing here. Now, the last lesson you got told that this is called the direction vector. So this is the direction vector. And the thing that's times by a letter is called the direction vector. So here, that's times by a letter. This is my direction vector, the 4 and the 1. So what you're looking at is the first direction vector, d1 I'm going to write, is minus 2, 5. And d2, what's that? It's 4, 1. So you do top times top, and then you add on the bottom times bottom. So minus 2 times 4 is minus 8. And I'm going to add on the 5 times 1. 5 times 1 is 5. So that is minus 3. This is not equal to 0. Therefore, they're not perpendicular. That's what you're doing. Perpendicular. Remember, perpendicular means they're at right angles to each other. And essentially what we're saying is if you drew those two, I mean this one here, minus 2, 5, it goes 2 left and 5 up. That's what that vector is doing. So that vector is going roughly up in that direction. Now this one, 4, 1, goes 4 across and 1 up. Now, it's obviously not drawn to scale. Now, it looks pretty close to being perpendicular. If it was drawn to scale, perhaps we'd know that it wasn't quite perpendicular. It's close though. It does on my dodgy picture, it looks close. Now what about this one? Well, again, you look for the ones times by the letters. So this is my d1 vector. This is my d2 vector. And I'm going to times them together. So I'm going to do 3, 1 minus 4. And the posh way is to write the dot like that. It needs to be a dot as well. It can't be a times. And I'm going to check what I get. So top times top. 3 times 2 is 6. 1 times 2 is 2. So add on 2. And then add on. Now minus 4 times 2 is, it's a minus 8. They do equal 0. Yes, hurrah. So because it's 0, they are perpendicular. So just get in your head around that rule, and definitely write that rule down. It's a very, very useful property of two vectors, and these two vectors are two-dimensional, but they can be three-dimensional, as my example showed you there. So that's a little starter that we've kind of touched on in the past in the exercise 2a, but we've done it a bit more properly there. Cartesian equations. Look, Cartesian is a posh name for an equation that comes with a y and an x. Sometimes you've seen at GCSE this form, and at A-level maths we definitely see this form. Cartesian, by the way, comes from, well, look at that. It comes from a very famous philosopher called Descartes, D-E-C-A-R-T-E-S. And Descartes was a very famously said this line. He said, well, he said it in French, but in English he said, "I think, therefore I am." And there's a bit of philosophy for you on what do when you're doing this. That's what he said, and but he invented coordinates. So not only was he a philosopher, he was also a mathematician. And I prefer his coordinates to his dodgy philosophy. So you can see that Descartes basically has been slightly abbreviated to Cartesian and Cartesian equations. So anyway, these Cartesian equations, notice we want y's and x's in them somehow. And we have already seen vector equations of a line are written in this form: r equals a plus lambda d. Sometimes we miss out the lines underneath and just write r equals a plus lambda d. Or it could be td or sd or ad. It can't be a because I've already got used in a. But you understand this is just a number, whereas the others are all vectors. Now in 3 dimensions it's a bit harder, so we're definitely going to have to work hard on those 3-dimensional ones. Let's have a look at this then. So it says to find the Cartesian equation of a line, write the x, y and the z, well, it might only be x and y, in terms of lambda, given all 3 equations. Rearrange it to make lambda the subject in each equation, and then just write it in this rather peculiar form. So here's my example. Now remember, r basically means x, y, and z is equal to this, is equal to this. So you can go along the top line, you can say, well, therefore x equals 1 plus the third lambda. This is what I mean by make 3 equations. Middle line, y equals a half plus 5 lambda. And the bottom line says z equals, well, it says minus 3 plus, oh, no lambda. Oh, well, z equals minus 3 then. Oh, I like that a lot. Now, what we're looking for then is these statements that basically rearrange these and get lambda equals. So the first thing I'm going to do is move the 1 over. So that gives me x minus 1 equals a third lambda. And then I've got to move the 3 over, and that gives me 3x minus 3 when I times everything by 3 equals lambda. That is actually done. And this one, what do I do? Well, I do y minus a half equals 5 lambda, and then I divide by 5. Well, if I divide by 5, I don't like this y minus a half, to be honest. I'm going to double everything. I'm going to go right 2y minus 1 equals 10 lambda. And the reason why I prefer that, now I can write 2y minus 1 over 10 equals lambda. But I could have written instead 1 minus half over 5. It's the same thing. I don't like a fraction within a fraction. That's really what I'm getting at. So notice how I then combine these. It's like this, but I've got a little complication of one of them didn't need it at all. It just said z equals minus 3. This is my equation now. I write 2 of them. 3x minus 3. Notice I simplified it but left it over 1. How weird is that? I can do that. To be honest, I don't really need that. Don't worry about that. Equals 2y minus 1 over 10. I'm happy with that because I did the same trick. That because the last one's different, we just say and z, by the way, is always equal to minus 3. Next question then, if I can find my pen. There it is. It's still the same idea, but now, notice last time we went from vector to Cartesian. Now it says, what if you start with a Cartesian and go a vector? Well, it says set each of the 3 expressions equal to lambda. So the assumption is, first of all, that this is all equal to lambda, each of these, and then you rearrange it, and then you finally get your r. So here I've got x is minus 2. Well, that one's just great. We like that. This one, 3y plus 1 over 4. Well, I'm going to have to write that equal to lambda. 3y plus 1 over 4 equals lambda. And the next one is 2 minus z over 5 equals lambda. Now, I rearrange it to get, in this case, y equals, in this case, z equals. So move the 4, I get 3y plus 1 equals 4 lambda. You can see I move the 1 on the other side. 3y equals 4 lambda minus 1. And finally, y equals 4 thirds. And you're probably better off writing it like this, minus 1 third, rather than all over 3, because I'm going to have to separate it otherwise. This one, I've got 2 minus z over 5. Move the 5 over, I get 2 minus z equals 5 lambda. But I want z equals, so I'm going to switch these two things around. I get 2 minus 5 lambda equals z. And again, I think I'm probably better off writing z equals, well, either one of them is in the wrong order. I've just realized it's actually this one is in the wrong order. You tend to want to write your number first. Minus a third plus 4/3 lambda. Now that may seem the wrong way round, but and this one now I'm going to write z equals 2 minus 5 lambda. This one, by the way, just says x is minus 2, so I could cheat and write x equals minus 2 plus no lambda. All of them should have lambdas. So what's this mean in terms of the equation? It means r equals, I write my x number first, minus 2 plus how many lambdas? No lambdas. My y, well, that's minus a third. How many lambdas? 4/3. And 2 minus 5y, so 2 and minus 5. Now, it doesn't mean it's the only one, but that, I suspect, is what I've got as my answer. And that is perfect. Dong. In 2 dimensions, find a Cartesian equation on the line with a vector equation that. So exactly the same, but now there's only 2 dimensions. But notice again, I can just write xy equals. So I can say x equals 2 plus lambda. I can say y equals 4 plus 3 lambda. Quite nice, this, isn't it? Lambda equals then x minus 2. And what's this one going to be? This is going to be miles away there. Y minus 4 equals 3 lambda. It really was miles away. Move the 3 over, I get y minus 4 divided by 3. So all that is true, apart from, well, fair enough, but the lambda is lambda. So I can just finish now by writing x minus 2 equals y minus 4 over 3. Now, is that the way we normally write it? No, of course it's not. So I could now write it in the form y equals. Move the 3, gives me 3x minus 6 equals y minus 4. If I move the 4 over, it becomes a plus 4. I reckon y is 3x minus 2. Y equals, underneath that, I promise you, it says y equals 3x minus 2. You can't quite see it. But this is the answer. Of course, you could go the other way round. Y equals 7x minus 2. Now, there's actually a quicker way of doing this. I mean, if we just cast our minds back on this one, what did we do? We wrote all of them equal to lambda and then kind of worked out the equation. So theoretically, we can do it here as well. So I say all of them. Now there's only one equation. I suppose it's a little bit more tricky, isn't it? So instead, think of this 7 as going 1 across 7 up. And as soon as you think of that as going 1 across 7 up, suddenly you've got a direction vector. My D, if you like, is 1 across 7 up. It's always, by the way, 1 across. That's what this gradient means. It means it goes 1 across for every, if it's 3x, it would be 1 across 3 up. If it was 19x, it would be 1 across 19x. If it was minus 2x, it would be 1 across 2 down. It's always 1 across and the number of the x, up or down. That's my direction vector. Now, the point where it crosses the line, if you think about this, the minus 2 is actually a point on the line. In fact, the axis there, it's a very steep graph, this one, and it crosses, not my best graph ever, at minus 2. Now, that has properly got a coordinate of 0, minus 2. So this really, well, I'm just going to write it. R equals, it goes through the point 0, minus 2, there it is, plus lambda, well, 1, 7. And once you realize that, it's actually quite easy. You find the y-intercept will always be 0, something, and the gradient will always be 1 something. There you go. Put a lambda in the middle and a plus, and you're sorted. So 0. Oh, look at that. So you even got a mistake on that. I feel bad. And 1, 7. There you go. Now their answer matches mine, and my answer is right. Look, exercise 2b. Then that's what I want you to do in class, and I think that should be okay. I think it's quite a nice little exercise.